Okay, so today we have two speakers, Professor Manjian Pei and you. So this is a topic about free boundary problems in transonic flow. So two parts. Maybe you start.
Okay. So thank you, Professor Chen. So first, I would like to express my gratitude for the Newton Institute for inviting me and then stay here. So I've been staying here for about a month, and then I have been sitting in the many great talks. So I got a lot of inspiration. I'm very happy. Also, I'm also very honored to get a chance to give a talk today because I'm leaving the day after tomorrow. Okay, yes. I also need to point out that I haven't been to many institutes yet, but so far this is the best institute I have stayed in many reasons. First of all, many great talks, many great people, good environment to work. Also, while I'm staying here, I was working on some particular problem. If I have time, I may present a little bit later. And actually, I got a good new idea how to approach that problem while I'm working here, so which is also a very good point. Okay, so today, I was asked to give a very introductory talk about what we are working, and then after I'm sitting in many talks, I realized that maybe the subject that I will present today is quite different from maybe what most people are working on in this room. But also I found some kind of remote connection, so maybe after I give this talk, if you can give me some kind of new possible approach or idea, that will be great. Okay. So today I plan to go back and forth between slide and Blackboard so that I can somehow give more really introductory talk. Also, please feel free to interrupt me if you have any questions or comments. Another thing, so according to schedule, I was asked to give hour and 45-minute talk. But if I execute that, fully, I may become a public enemy before I leave. So I will try to somehow shorten the time. Okay, so let's see how it goes. All right, so, well, here, everybody knows what free boundary problem is. So maybe today my focus should be to explain how somehow this so-called transonic flow comes into some kind of free boundary problem study. All right, so this is just outline. Just to give you some briefly the idea what I will talk about today. Well, in the study of transonic flow, especially if we are studying some kind of a discontinuous transition for compressible flow, the most important thing that we have to know first is Rankine-Hugoniot conditions. Probably many of you already know what it is, but I will explain this again today. And then, well, first of all, this Rankine-Hugoniot condition comes from conservation law. And of course, conservation law can be mathematically formulated in different physical situations. So among them today, I will focus on compressible flow with no viscosity, in which case the flow motion is governed by the Euler system. Even for a Euler system, so I will show you the formulation in a minute, but you will see that the system itself is also quite complicated, also nonlinear. So sometimes we have to simplify the system, which comes as the form of isentropic Euler system. And for the study of a multidimensional case, we also work with the potential flow a lot. So I will also explain the difference or how we formulate this today. And then eventually, of course, I will come to the parts to explain how somehow this transonic flow related to the Euler system can be formulated to free boundary problems. And also, I will also take very simple example to show you how we actually solve the problem. And then also, you may give me some feedback about this to improve our method. Because currently, our method is restricted to the case of a small perturbation, except for very special case. And then finally, I will also explain, I will also give you some open problem. One of the open problems, which is widely open and is very important in general. Okay, so I already said a lot of words which are already here. So if I take the compressible flow, which means that the density of the flow is not constant, and then if I take off the viscosity, then of course there is no smoothing effect in the flow, so therefore we expect some discontinuous transition happens in the flow, which we call shock or contact discontinuity. So I will also explain the difference between those two subjects. And again, those two are prescribed by so-called Rankin-Hugoniot jump condition. So first thing that I have to do is to explain what is a Rankin-Hugoniot condition and how we use it in the study of a free boundary problem. Okay, so quite simple formula that we can derive. Well, probably many of you already know, but anyway, I will go through to give you the idea. All right, so we just, first of all, we consider this flow motion in Eulerian coordinates, which means that we take some space and we just observe the flow going through here, okay? And then, generally, the flow motion is prescribed by some conservation law. So at this moment, we assume no external force. So the conservation law will be given by this form. Or for more general form, well, you see, this also we can just write as divergence free vector field, just for simplicity. So I will just use this form. So sometimes this can be considered the steady conservation law, or even the general conservation law can be written in this form anyway. Okay, so I observe some flow, and then somehow suppose that there is some kind of a drastic change in the physical quantity of the flow. Well, for example, we can imagine that the flow velocity just drops down suddenly, or the pressure just increases suddenly, something like that. So across this boundary gamma, which means that away from the gamma, our flow is smooth. So therefore, the flow will just satisfy this equation in a classical sense. But across, well, at this gamma, somehow there is discontinuity. So we have to somehow prescribe this as a solution of a PDE. But of course, very naturally, since our equation is in divergent structure, we can naturally derive the weak formulation by integration by parts. So the definition of the weak solution for this equation is just given by this weak formulation. This we already know what it is, basically given by integration by parts, right? Okay, also our assumption, so Q is a classical solution in omega minus and omega plus, but there is a discontinuity here. Overall, it's an L2 function, so that we can actually satisfy this relation. Okay, if that is the case, we can take the integration by parts from here, because in each of omega minus and omega plus, our solutions are regular, so we can do the integration by parts separately, right? Okay, if that is the case, if we do that, so here, for example, in omega plus, we do the integration by parts, which means that, so this is integration by parts, right? Okay, maybe they are experts, so maybe everybody knows what it is, right? So if this one, but even so, I will just write it out. So integral Q dot grad phi equals to integral divergence Q phi, right, minus divergence Q phi. Say where this is omega plus or omega minus, right? Then we apply divergence theorem. Then this becomes the boundary omega minus. We have Q dot n, where n is the outward normal vector times phi. So we do this integration by parts in omega plus and omega minus. When we do that, so here the normal vector, so if you look at this normal vector in omega minus side, since it's pointing outside of omega minus, actually the direction is pointing into omega plus. But if we do the integration by parts in omega plus again, then the outward normal vector will point into omega minus. So their directions are opposite. So if we do the integration by parts in each of omega plus minus and combine them, so this is the result that we get. So here the bracket means that, so here n is basically the normal vector on gamma pointing toward the omega plus. Then, well, in each there, so by the integration by parts, what we get on this boundary integral part is the difference of this normal component of Q on gamma. Okay? Because here and there, the normal vector point in the opposite directions. So from now on, if you see this bracket, means that we take the difference of the limit value from two sides on this boundary gamma. Okay, then if our solution is a weak solution across, But classical solution in each of omega plus and omega minus, then of course, well, this jump condition must hold. So that's exactly the Rankine-Hugoniot condition. Okay, so this is just derived from the general conservation law. So if we apply this to Euler system, then we get a whole bunch of Rankine-Hugoniot conditions coupled with the Euler system. Okay? All right, so here's the Euler system. So the full formulation is over here. So here rho presents the density, and the U is the velocity vector field, and P is the pressure. So if we consider this n-dimensional flow, here the spatial dimension is n, then we have n plus 2 unknowns, also n plus 2 equations. So the first one, well, prescribed mass conservation law. So we assume there is no other external force. So the second one is a conservation of a momentum. But if you look this closely, this actually consists of n equations because U is the velocity vector field. And then the third one is a conservation of energy. So here E represents internal energy of the system. Of course, well, we cannot consider E as independent one because we need to close the system. So and the E actually are given by some physical property of the gas. So in particular, if, well, from now on, I will restrict our interest to the case where this internal energy is given by this constitutive relation. So E is basically a function of a pressure and density, where it's given by this algebraic relation, and gamma is just a constant greater than 1. We call it adiabatic exponent. So physical function. Okay. Well, why do we study that? Because well, one of the things air is falling into this category. Okay, so if we put it there, we close the system. So this is our Euler system. Well, of course, if you close the whole system, unsteady Euler system, the systems are very huge and hard to deal with. At this moment, what many people do in our field is first to consider the steady case. So I will just put our interest in the steady case at the moment. But if you have any idea about how to approach the unsteady case, I also welcome to listen to your opinion. All right, so while we proceed, one of the quantity that I would like to put some focus on is this quantity, which we call so-called the Bernoulli's invariant. Invariant means that something's not changing, so what's not changing? So I will explain this later. So Bernoulli invariant is basically this part, the kind of a flux density of the energy, which is right over here. And I will explain why this we call invariant. Okay, so take the Euler system, which is in the conservation law form, so that we can also consider, okay. Oh yes, now I have to explain. So, okay, so this is Euler system. And then if you study this in multidimensional case, like I said, for example, if you study this in three-dimensional case, you have 5 equations to deal with, nonlinear system, too complicated. So still, many people prefer to use the simplified system. So now, since this is an introductory talk, I may use this opportunity to give you some kind of simplification of this Euler system. And also, okay, at this moment, the only case where one can study this full Euler system is when the spatial dimension is 2, where you have 4 equations. So I believe that Haidong will give a talk about that in more details. So at this moment, I also, currently, I mostly work on the multidimensional case, where the spatial dimension is 3 or higher. So in that sense, I will introduce you some simplified model. Okay, maybe I still need this one. Okay, all right. So in order to explain that, now if you take the momentum equation, so let's look at the second equation more carefully. And then if you look at that, really calculus, but I will do it anyway. So rho U times the product U plus P. So this is n by n matrix, identity matrix. This is equal to 0 on one side, right? And then if you assume your solution is C1 and everything, so product will apply, then this we can write as divergence of rho u times u, and then rho u dot product with the gradient u. Then of course it becomes m by n matrix, and plus gradient of p, right? So what we do is that first, so from the mass conservation, this is already 0. So this is 0. And then second, we just take the dot product of this with the velocity vector field to reduce this to scalar equation. Okay. Then what happens is that if you take this times that, so you take the dot product of this with that, and then plus grad p dot u. Then you can actually reduce this down to the following. Okay, times u. Okay. So this is just calculus. One can directly check, and plus this. Okay, all right. Then how can I further simplify? Now I also restrict myself for the non-vacuum space, which means that I assume the density is strictly positive all the time. So therefore, if the density somehow becomes 0 somewhere, I also need to be extra careful. But at this moment, assume that the density is strictly positive. Then I can do the following. So rho, and then for this one, I have a gradient of. So if you remember the Bernoulli invariant that I introduced at the beginning, so the Bernoulli invariant is this. For our case. So therefore, which means that, so I'm very sorry that I'm going through all this detailed calculus in front of this great mathematician, but please forgive me. But just to give you the enough motivation why we are studying this kind of a special model that I will show you in a minute. Okay, so I
forgive you if you explain to me something. This funny Greek letter is gamma or lambda?
Oh, I'm sorry, my writing terrible. So this is a gamma in my writing. Yeah, my advisor taught me how I should write gamma, but I never.
It is difficult to believe.
Okay. I'm very sorry. Okay, I will try to fix it next time. All right. So okay, I just replace this by that. Okay. Then I have gradient of so b minus. Okay, so this is gamma. Still, I don't know how I should write. Gamma minus 1 rho. Okay, getting worse, I think. All right, so plus grad p over rho, dot product with u. Right? So it looks like getting worse, but in fact, it's not. So going back to here, you see, if you look at the energy equation, in fact, so the energy equation is in form of the divergence of rho u times b equal to 0. So again, by combining this with energy mass conservation, right, then you get rho u dot grad b equal to 0. So again, assuming non-vacuum state, we have the fact that this Bernoulli invariant b is preserved along the integral curve of the velocity vector field. Right? So we have this one. So that's why we call it B Bernoulli invariant, because it doesn't change in smooth solution along the flow direction. So therefore, in this expression, so this times that just disappear as a 0. Then actually you can simplify. You see you have inside, you simply have the expression of pressure and density. So if you just work hard from there, you end up with the following great results, which is, so this is rho u dot, now, So what does that mean? So this means that this quantity also invariant along flow direction. Okay? So therefore, from here, now I also should save this for later. So here we have u dot gradient of ln rho to the gamma over p equal to 0. We also have the relation that u dot grad v equals to 0. So these two comes from the fact that we assume non-vacuum states and C1 solution, right? So this actually has some special meaning, and we have a name for that. So in particular, we define the function s as p over rho to the gamma. And then the name of this, in fact, is entropy. Where, to be more precise, it's not exactly entropy according to physics, the definition to the physicist. The definition of physicist is that, in fact, if you take the log of this, so this particular quantity becomes the entropy, in fact. But somehow I found that this is much more convenient to us. So from now on, I will just call this as my entropy. Because what does that mean? Which means that if I take the C1 solution of Euler system, which then the entropy is always preserved along the integral curve, which we call streamline, of the flow direction. Which means that if we prescribe this entropy as a constant at the beginning, everywhere, which means that it will remain constant through the flow, right? Okay, so from that point of view, we can simplify the system by considering the case where we fix the entropy at the exit by a constant, which we call isentropic system. So from there, so if we assume, entropy, which is a p over rho to the gamma, it's some constant S naught. So S naught is a constant. So under this assumption, if you just write down the Euler system, then you get so-called isentropic Euler system. In which case, now we in that case see somehow, for example, if the density is given, the pressure is automatically determined, which means that in the new system you have to drop one equation to make the equation well defined. So now the equation we drop is the energy equation. So isentropic Euler system is the following. So we have divergence of rho u equal to 0, and we still keep the momentum equation. And then now the entropy just becomes algebraic function of the density. So we have S naught, rho to the gamma, identity matrix 0, and then no energy equation. So this is our isentropic Euler system.
And stationary.
Stationary, yes.
But you can do the same thing in non-stationary.
Yes, I think so. Yes. Okay. Now, so why do I really waste my time to explain isentropic Euler system? It's because we actually derive out so-called potential flow equation from the isentropic Euler system. So if you take the mass conservation law and momentum conservation law with assuming the entropy constant, and then plus. So this actually is still a good system, but for example, if you take three-dimensional flow, still you have 4 equations to handle with, which is still too much. So what do? If we want to study n-dimensional flow, so multi-dimensional flow, we're still, unfortunately, people put some more assumption, which is irrotationality. So we assume the vorticity of the flow becomes 0, which we can interpret as u is given by some gradient of a potential function. And the field we call velocity potential. So what do? we simply use this relation and plug this into isentropic Euler system. Then we get our potential flow equation. So let's write it out. And then actually there, in that case, not only you somehow simplify the system, after all, you just end up with a single equation for phi. Much better situation to work with, but still we can somehow study a lot of physical property of the shock that we will discuss today. All right, so what do? I just plug it in. Then, for the first equation of isentropic Euler system, I have divergence of rho, grad phi equal to 0, which is quite simple. Now the momentum equation becomes much better. So what happens? So I have divergence of rho phi, and then this one. So if you just go through the same procedure as before, so this actually is equivalent to, again, assuming all my solutions are regular and everything. So this I can rewrite as rho gradient of 1/2. So this is actually one of the nice properties that we can apply for potential flow. Somehow you can reduce this term into there, combining this with the mass conservation, and plus this one becomes S0 plus 0, which you can even simplify as the following. So what does that mean? This quantity becomes constant in this case. Right? Okay. So now we came to really nice equation to study. All right. So this we call so-called Bernoulli's law, after all, which implies that density, it simply becomes the function of the speed of the flow, which is the following. Okay, let me just write the following. Times some constant, but let me just normalize the constant to be 1 for simplicity. Then what happens? So here B not is a constant, by the way, which we can simply determine from the entrance data of the flow. So if we simply plug this into the first equation, after all, we end up with second order nonlinear equation for velocity potential phi, which is the following. So after this trivial computation, what we end up with is this equation. So from now on, my focus is to study solution of this equation. Okay. All right. So yeah. Now, so since my interest is transonic flow, now it's time to play with the Rankine-Hugoniot condition. So first, we play with the Euler system to derive that simpler version of the equation, but still useful to study multidimensional flow. What about the Rankine-Hugoniot condition, right? Okay. Yeah. So here's a Rankine-Hugoniot condition. So again, just by following the computation that I showed you for the general conservation law, just do the integration by parts and everything. For each equation here, then this is the Rankine-Hugoniot condition that you find. So when you actually solve the problem of a transonic flow, what you have to do is to find out the solution of this so that in each of omega minus and omega plus, it becomes the classical solution. But also at the same time, you have to figure out the location of this gamma, where this continuous transition happens, so that on gamma, this Rankine-Hugoniot condition satisfied. So that's why this problem becomes the free boundary problem. Because you have somehow unknown boundary, which you have to find simultaneously together with the solution itself. Okay? So this is the Rankine-Hugoniot condition for the full Euler system. So in a minute, I will also write down the corresponding Rankine-Hugoniot condition for potential as well. But before we do that, so if I'm sorry? Oh, B is the Bernoulli invariant that I, so B is this quantity exactly. I just use this notation for simplicity, yes.
Yeah, the question is, so you have a system for this rotational flow.
Do we have?
You have an equation for this.
Yes, we have the equation.
Why do you need a free boundary?
Okay, so this I will explain.
Okay.
In the so very good question. That's the whole point of my talk today. Yes. Okay.
You may mention also incompressible flow, incompressible Euler equation also from here.
Right.
When the curl equals zero, other density more zero, constant.
Okay, so
And
the
you got two conditions,
Yeah.
different kind of conditions. One is incompressible, one is potential.
okay, but I'll move on and then
Right,
let's
yeah,
see
why-
if somehow my talk answers
Yes,
this
yeah,
question.
complex.
I think it will anyway. All right, Rankine-Hugoniot condition. Now, in fact, eventually I will show you the example, physical example of the problem that I'm considering. But before we do that, we need to explain, we need to understand somehow how this gives us some physically interesting phenomena. Before that, let me actually take more closer look at this is second Rankine-Hugoniot condition coming from the momentum equation. Okay, another calculus. As you can see, this is the vector. This is a vector. So this is typo. So here n is the unit normal vector on gamma. So you can ignore the sub-index s. So this is a vector. So therefore, we can take the dot product of this with a tangential vector on the gamma, which will give us this result. If you take the dot product of this with the normal vector, you get this result. So somehow this equation, this jump condition equivalent to this set of jump conditions. Now, we take look at this one. So this is a product of two quantity. So here, one of the reasons I pull out this rho times the normal component of velocity is because I have this balance law coming from the mass conservation law. So anyway, the normal density flux is preserved along the across the gamma. So they are same on the both sides. So that's why I pull out that way. Then in order to satisfy this equation, I have two cases that I can consider. Since I'm assuming rho positive, which means either this normal component of the velocity vanish on gamma or does not vanish, in which case this jump of a tangential component of velocity on gamma should balanced. So we have two cases. Okay? First case, when the normal component of velocity vector does not vanish, so this is the case where we call a shock physically. If this vanish, so this vanish, so therefore, if the jump of tangential component of velocity is allowed, then this is the case where we get so-called contact discontinuity. And this is another name for the vortex shoots, if you are familiar with that terminology already. So we have two cases, in fact. Today, I will more focus on the case of a shock. But in fact, actually, there are many open problems in which both shock and contact discontinuity appears, and they interact at one point.
Sorry, I lost with the notation. What is the difference between N and N sub S?
Oh, so that actually, as I said earlier, you can ignore S here. NS equals N. It's a simple typo, and they are unit normal vector on gamma. And tau is the unit tangential vector, gamma. Okay? All right. Yes. So where shock happens? So this is the example of the shock. But somehow you don't see the dynamics here. So I brought the movie. And this is the selling point of my talk, I think. So this is the movie that I stole from YouTube. The space shuttle is being launched from the ground. So now you really need to pay attention here. The shock is really very tiny picture. So at this moment, nothing happens, right? Very clean shape. Now it runs and it will get accelerated. Nothing happens yet. Keep going. All right. Now cloud somehow blocked us, but it's okay. Okay, wait. Now finally, okay. Okay, now nothing happens. You start seeing some kind of, okay, let's wait. Oh, yeah, some cloud forming around the body, right? So this is a shock effect. Because it somehow speed up. The speed almost reach a Mach number, then you start seeing the shock. Yeah, so somehow, stays, right? Also, like this somehow, all of a sudden, you start seeing another shock. Okay, just once, right? Okay.
So you see the shock when it becomes hyperbolic?
That's a very good question. So for the shock, we have two cases. When the state in front and behind the shock supersonic, but one state becomes supersonic, the other state becomes subsonic. So this actually is the case probably you may be interested, because there you have a mixed type equation. One side your equation hyperbolic, the other side elliptic, you have a free boundary in between. So that is the problem that I will present today. All right, so actually this probably I can start answering your question. So why we study, so when we study this potential flow equation, why we need a Rankine-Hugoniot condition and so on, right? Okay. First of all, I have to mention that this equation is not elliptic nor hyperbolic. They can be both, depending on the size of a gradient. And here is the computation. So I take this potential flow equation here, and then I assume non-vacuum, which means that this quantity basically is the density to the power. So this quantity positive in the divergence form. But if I just apply product rule and just rewrite this in non-divergence form, then I can start to look at the coefficient matrix there. So actually, I also computed these coefficients of the equation. So here, you can ignore big phi. So this appears when I study all Poisson system, which is another interesting case. But unfortunately, today I will not be able to talk about it. So ignore this phi. Just coefficient that depends on the gradient of velocity potential, where you have this expression. So this comes from direct computation. Delta ij, Kronecker delta ij. Just if ij is same, 1, otherwise 0. Okay, then. Now, let's see what happens for the type of equation. So first of all, our equation is the divergent structure, and that only depends on the gradient, which means that this equation is invariant under translation and rotation, everything. All right, so using that property, let's fix a point, a certain point, and then let's look at the size of a gradient. So if the gradient is 0, then coefficient always positive becomes elliptic. So what if the gradient is non-zero? Then by doing some rotation and translation, I can introduce new coordinate where the given point becomes the origin, and then the gradient vector simply becomes the vector in nth direction, right? Okay, so if I write down my equation in these coordinates, then my coefficient has the following form. So first of all, if I and j are different, becomes 0, right? If I and j are same, I have two cases. If j is less than n, it becomes b naught, which is given, always positive. If j equals to n, then I have this relation. So depending on the size of a gradient, this can be positive or this can be negative. Right? Okay. So using this one, if I write down my equation, again, I have this relation. So some part always Laplacian, but this is not positive. You can change the sign. So if this is a positive, you have elliptic equation. But if this is a negative, then you have some kind of nonlinear wave equation, which is hyperbolic. Okay, so it's a mixed type, and then the type depends on the gradient. So in terms of a physical interpretation, that means that, so remember the gradient of a potential is the velocity. So the size of a gradient is big, which means that the speed is fast. So if you have supersonic flow, your equation becomes hyperbolic. If your speed is small, so therefore you have a subsonic flow, then your equation becomes elliptic. So if you start seeing a shock, where on one side hyperbolic, the other side, one side supersonic, the other side subsonic, that means that you have to deal with a mixed type equation so that in one area it becomes hyperbolic, the other area elliptic. You have to figure out the location of free boundary so the Rankine-Hugoniot condition holds. But of course, I haven't shown you the Rankine-Hugoniot condition for potential flow equation, so I will explain about this in a minute. Okay, so I just explained this. All right, so now back to the blackboard. So what is the Rankine-Hugoniot condition for the potential flow equation then? It's quite simple, just by looking at the divergence structure, and then you just do the same argument as we did on the conservation law. So simply what I have to do is to take the dot product of this quantity with a unit normal vector on this boundary. So this, if this is my density flux, then I have to dot product with n, which is a unit normal vector of the boundary where this continuous transition is happening. And then I take the difference on both sides. Right? Very straightforward. The question, is this enough? So far, I only have one equation. So according to this conservation law, I can only have one jump condition. But is this enough? Okay. So suppose that you have elliptic equation, right? So you have some gamma, and you have some domain where the flow is subsonic, so therefore you have elliptic equation. Okay, but this is a free boundary. Okay, so if I have this, suppose the gamma is known somehow, then what does this do? So this will tell me the boundary condition over here for my elliptic equation. Then where this free boundary comes from, right? Still something missing. Why? Now we need a physical observation. Physicist I. I'm assuming irrotational flow, right? So the only discontinuous transition that I can consider at this moment is a shock. Vortex shift I cannot consider here because there is no vorticity there, right? So which means that only boundary gamma that I consider is a shock, which means tangential component. So the tau is the tangential vector on gamma. So tangential components of the velocity should be balanced on both sides, which means that tangential derivative of phi on both sides should be same, which means the difference of potential on both sides should be a constant. So for simplicity, without loss of generality also, from that point of view, we assume the continuity of potential function on gamma. So after all, this will become free boundary condition. Okay? All right. So Professor Chen told me that I can take maybe short 5-minute break because everybody seems to be really getting boring now. So if you like, you can ask me a question and then maybe we can resume at 255.
But it was not boring.
I'm sorry?
It was not boring.
It was not right. But maybe let's take 5-minute break, and maybe if you have any question, we can discuss. Yes. So I will resume at 2.
So let me ask you this question.
Yes.
Suppose that then you say you don't have this constant fee. What happens?
A constant fee.
If fee is not constant, you are putting some difference in the tangential velocities.
Right,
This
then.
creates a certain turbulence.
Oh yes, exactly. So, but in that case, of working in the potential flow scheme is not work. But anyway, so if so the gamma, suppose that so the question you asked is the case where this normal component of velocity vanish. In this case, what happens is that if you fix a point on one side, okay, suppose that the flow goes like parallel to gamma, and the other side still goes parallel to gamma, but size different. It can go the other direction, doesn't matter, right? So if you particle there, somehow it will start rotating, which means it's generating vorticity.
So this is like a Taylor-Chapman instability? They will get an instability there?
Yeah.
It is. There is instability there.
So this is not considered because it's a rotation.
Yes, because here this is a rotation, and we cannot consider rotation in the potential flow case.
Okay. And now, second question, just practical. You show this movie.
Yes.
So there's the shuttle going up.
Yes.
Are you assuming that the movement of the shuttle is rotational around it?
Yes,
Is
there
it
are
reasonable?
rotation. So in general, our general understanding is if there is a shock, normally the vortex is generated. In general case, I believe. So, but even so, we study potential flow just to get nice just understanding about the shock structure. Yes. Okay, so maybe we should take 5-minute break, right? So we'll resume at 55.
Yeah, it took us 1 minute.
We need 5 minutes. I've been paying attention. Right? We need a break. Okay, good. Yeah, I like this.
Slow down, just
the
stop.
curious that in the end of this thing, you get this gradient diffusion, gradient dependent diffusion equation.
Yeah, yeah.
And the point is that now it can change sign.
Not a defect. No, it's
It is.
hyperbolic.
No, if you don't go to the, if you don't go to the,
Exactly.
if you don't go to the hyperbolic, it's
So what is the method of iteration? Well, since here the perturbation of the wall is a kind of smooth, if I measure the size of the perturbation by some norm given in Banach space, and suppose that the perturbation size is sigma is quite small, then I can also expect my solution phi is quite close to the given one-dimensional solution there, so which I will call phi plus, right, which I can also easily
Where does
compute.
gamma begin?
I'm sorry?
The peak curve, where does gamma begin?
Gamma, so we have to find it.
But do you say that its endpoints are on the flat boundaries? Is that a fixed point?
No, okay, it's not fixed.
That's got to be
No,
found.
it's moving.
to be
That's
found.
fine. Yes, completely fine there.
It has to be found.
Yeah, it has to be fine.
Orthogonal.
We have to actually find to set it.
Shifting, yeah.
Yes.
This has to be determined.
So later, if I'm sorry.
it is orthogonal.
Yeah, orthogonal, yeah.
Yes. Also, in this case, because of slip boundary condition, we know that it may look like this near.
If you didn't make the assumption about gamma,
I see. Okay,
and
well, I see
start
what you
with it
mean.
and you start with the problem on a large rectangle,
Right.
then can you say that weak solutions that there is? I don't really go for uniqueness.
Okay, I see. The uniqueness is just a very important question. So, in this case, for this particular problem, those boundary conditions we put here, just for simplicity, it is something like that. So here, phi plus is a given one-dimensional solution. So we just match this with the phi, just give a Dirichlet boundary condition. In that case, we can locate the unique location of gamma, but in certain class, the class that I will write down over here. Okay. But in this case, of course, if you put some physical boundary conditions, such as if you prescribe the pressure, for example, there, then this problem will post. Either you have an infinitely many solution or no
And
solution.
if you let the tube go to infinity?
If you let the tube flat. Yes, if you have a different geometry, of course, then the physics
But
different.
suppose that you have wiggles and you get the tube go to infinity. You still
Yeah.
have
Oh, so cube go to infinity, same. So if you somehow prescribe, because even for the unbounded domain, you will leave the problem. So if you prescribe some kind of asymptotic behavior there, the rule is exactly the same as judicially boundary condition. You just need some kind of asymptotic estimate. Still, for this judicial type boundary condition, you can locate the unique location in some class, where the class where I will write down. So here, in this case, the solution I expect is some kind of a small perturbation of this one-dimensional solution. So there, when I do the iteration, I need iteration set. In the set, I construct some mapping, and in the mapping, I find the fixed point, which will give me the solution of that. So the space I consider, I take the difference of my one-dimensional from one-dimensional solution. I take any function in certain space, some known in the Banach space, something very small. So here sigma is exactly the size of a perturbation. Then I of course expect my perturbation of solution from the one-dimensional space not exactly sigma, but somehow relatively comparable to sigma. Okay, this is the space that I'm working on. Then what I can do is that, so here this I will call K, and of course, in the process of iteration, I also need to choose M very carefully, because eventually I will use the fixed point theorem, which means that I need some kind of compactness, which requires some kind of a priority estimates. I need to make sure that my iteration mapping maps any element in K into K again, so that I can have a fixed point. So that's how I choose M anyway. But so of course, when you do that, it's related to the elliptic estimate, right? Okay. Now about the free boundary problem, because here your common interest is a free boundary problem. So how do we locate this guy then? All right. The idea is the following. So I fix a phi in K. Okay. So I start with phi. So I consider this as my approximate solution. So then somehow, using this, we also find approximate location of a shaft by finding the zero level set of phi minus phi minus equal to 0. So I solve this. Okay. But here, one has to remember that so how do we find the zero level set over there? Then, okay, so if you look at the derivative difference in xn direction, right? So you see this phi is sufficiently close to phi plus in some Banach space norm. Somehow we need to still control the gradient size of there, because the coefficient depends on the gradient, okay? So if the gradient difference there is sufficiently small, then this is like, so the derivative in n direction of a phi is quite close to u1 there, if you believe me, and the derivative of phi minus is u0. And of course, there is some error, which I will call plus minus m sigma. So if this m sigma, say, it is sufficiently small, like 1/10 of u0 minus u1, because u0 big, right? Then this is certainly non-zero, which means that you can apply implicit mapping theorem. So by implicit mapping theorem, there exists unique function f phi, so that becomes 0, right? So now I fix the location of gamma here, which will give me fixed domain. There I start solving the elliptic equation as well. So when you solve the elliptic equation, well, probably I will not be able to talk more details. But if you're interested, I will be happy to discuss later. But let me just add one remark. So somehow this problem, so you fix somehow gamma phi. And then now you have elliptic equation to solve. The equation to solve. Here you have divisional boundary condition, fine. You have Neumann type boundary condition, fine. Now what about the boundary condition here? As I said earlier, you have another boundary condition coming from Rinkin-Hugoniot condition, right? Important thing is this normal vector n. Of course, if by looking at this, oh, it's a Neumann type, so you can just give somehow Neumann type boundary condition, but one has to be very careful because when you solve the equation, we just don't solve this nonlinear elliptic equation. We are also here, we linearize the equation at given approximate states, and so on, right? But when you do that, you also have to linearize the boundary condition on the shock. But what about this guy? How do you linearize this guy? There, you also need to remember that this, you have this relation, the normal vector, right? So since since gamma here is a zero level set of the difference, the potential on two different sides, normal vector also given by this form. So you plug this into here and you linearize. And then solve the problem and continue the iteration. The details, of course, can be found in many literatures. So, I mean, about how we solve this problem exactly, maybe I think that this is good enough. But if you have more questions, I will be happy to discuss with you. Because now, I want to call your attention to this open problem. Because I promise you that I will talk less than 30 minutes. Oh, okay. I'm doing a lot of exercise today, which I need. Okay, so that's the iteration that anyway I covered a little bit. Okay, now, what's the problem that we can work on? So at this moment, somehow, there are still many open problems in, even for potential flow problem, right? And one of the problem is the following. And this problem, I will really happy to listen to your opinion about how we approach this problem. Situations is the following. So imagine now your nodule is no longer flat nodule, different geometry. So your nodule looking like this. So where does it come from? If you look at the rocket where the engine nodule looks like this. Yeah, engine, whatever, where some parts of the rocket has this shape of the nose, I have to say, okay? And then you can just imagine the flow coming through. And then we are studying how this flow changes in time. Okay, so the graph on the top explains the cross-section area of the nodule as you go through. Next, so this is x direction. So as you can see, up to the throat, the cross-section is decreasing, which means shrinking. And then after that, it's expanding again, right? The bottom graph explains how the pressure changes throughout. And still, even this graph is given by some kind of approximate one-dimensional analysis. It's not complete analysis. We only just have a brief idea about how the flow will change. And this needs to be verified still. The graph is the following. So this is the pressure, and this again, the pressure throughout the nozzle. And then this P star line represents the state where you have a sonic flow. Above it, you have high pressure, which is a slow flow. So this is subsonic. Below, you have a supersonic. Okay. Now you start with the same pressure at the entrance, but at the exit, you put different pressure, and you see how the pressure changes throughout. Suppose that at the exit, you put the pressure very low, sufficiently low. Then starting with the high pressure, pressure decreasing, which means the velocity increasing, getting accelerated. At a certain point, you have a sonic state. And then go through, and then smoothly changing to supersonic state. So it's gradually just accelerated. Now, another interesting case is the case where pressure is right over here, right? Now, somehow in this convergent part, somehow pressure decreasing, which means that it's accelerated, pass through the sonic point. Actually, the figuring out the sonic point is also another interesting free boundary problem, in fact. And then you just turn into supersonic area, getting very fast. But then, at the exit, you put the high pressure, so which means the flow should suddenly drop, the speed drop down. And then you get a shock, transonic shock, right? So figuring out this picture, so first of all, for this case, let me point out, earlier example, I construct one-dimensional solution by solving ODE. Here, we don't have ODE setting. So we don't even have some kind of a solution with a simple structure, okay? So therefore, talking about stability is a very fast story. So to also give you some idea, I also have another movie, which again, I stole from YouTube. It's amazing, you know, what you can get from YouTube these days. Okay, so here, this is not the computation that I did, stolen from YouTube. So the blue, the blue is very slow. So this is like the zero velocity. The red is really fast. So you see that here, it's getting accelerated. Somehow green zone is somewhere you have a sonic boundary, which means that your speed becomes sonic. In terms of the equation, you have an elliptic equation, but it becomes degenerate. And then it's smoothly changing to supersonic, which means hyperbolic equation. And then somewhere here, because of high pressure, you also have some shock. So the question, how do we figure out this boundary, sonic boundary, where your speed becomes sonic? That's extremely difficult question because you have an elliptic equation with a degenerate boundary, but this degenerate boundary is free boundary also. So this also we have to figure out, but we have no idea. This previous approach will not work because anyway, it's a smooth boundary. Maybe here earlier to figure out the transonic shock, we only look at zero level set of a potential function. Now here you may have to look at some kind of level set of a gradient function. It's a kind of difficult to figure out. Also, the location of a shock, also finding location of a shock in divergent nozzle, open problem. So
you mean that this movie in YouTube is simulated numerically or just from experiment?
Well, this I found from YouTube, so I cannot say it. But I believe this is some kind of numerical computation. Yes, not the...
So they can solve it?
I think so.
Numerically?
Yes, numerically, yes. All right,
it's
so...
interesting because this new free boundary is completely blurred.
Yes, maybe because here, because there may have some kind of like a viscosity effect. This I'm really not expert, but considering that there is a shock with a thickness, which means there should be some viscosity effect, I think.
Which is reasonable?
I think so, because in nature, actually, when the shock happens, the flow becomes compressive, then you may see some viscosity.
So you don't see the free boundary, but you get the computation done is realistic.
Right. Okay. So this is a free boundary problem. So many different parts. So this is completely open. So anyone who's interested will be great to join the research in this field. So what did I do in that direction? So I also
is cylindrically symmetric.
Oh, so here we don't need to assume cylindrical symmetry here. So if you assume cylindrical symmetry, maybe one can reduce the problem to maybe for 3D, one can reduce the problem to 2D setting, right? So here still the difficulty is the same because when we approach to this transonic shock problem, what we usually do is that you first construct a solution with a very simple structure, say 1D structure, for example. But even in this case, if you reduce down to the 2D, still I don't think we can construct somehow a 1D structure solution. Still PD structure, I think. So here, the analysis given over there is given by some kind of assumption that everything just depends on x variable. But actually, in experiment, you see that it's not like the depending on one variable. Actually, it depends on many other variables in this case. So, okay. So actually, one of my thesis problem was in this direction. So at least what's done at this moment is that the nodule, actually, the realistic nodule case is when you have a curved boundary. But at this moment, what we can do is that this straight boundary in this case, because, well, you can assume your solution just depends on radial variable first, construct the radial solution, radially symmetric solution, and consider small perturbation. So that's actually what I did as my thesis problem. With a potential flow equation, important to see, just one quick comment, I almost finished. So here, what people usually use is this isentropic potential flow equation with one Rankine-Newtonian jump condition. But for this particular problem, what we put as a boundary condition at the exit is the pressure, which gives us nonlinear boundary condition, but more realistic. There, in order to get the well-posedness, assuming isentropic condition is really dangerous. You don't give a well-posedness there. So there, we really have to count in the effect of this jump of entropy. So there, I introduced so-called non-isentropic potential flow model. The equation, still you see the same equation, but now I have new equation. So therefore, I also have extra Rankine-Newtonian condition. Structure more complicated because it's somehow the equation of phi coupled with the p.
I don't remember.
Yeah.
B naught in this non-isentropic is a constant?
So here is still constant. B not oops. Yes, it's a constant.
Okay.
Now, but we don't assume. So here, the difference is
P
the
is
rho.
not an exact function of rho.
Right, so here the rho earlier only depend on this, but now in this new model, rho also depend on the entropies. So this is unknown here. So we also have to solve this by Transonic equation. So actually, there I did it. Also, so this is a multi-D case. In 2D case, with the full system, there is already known result in this straight nodule boundary. One of the results by Hairong Yuan, which who will talk in a minute, in 15 minutes, I think. So in 2D case, using the full order system, people can do a lot of things. But in multi-D case, still potential flow equations are the only equation that we can solve. So now, maybe it's a good time also, all of us also start thinking about how we can formulate this in multi-D case with the first system. There you have to work with the elliptic system, maybe. So probably I think maybe people in this room may have a better idea than us. Okay, I stop here, so thank you for your attention.
Well, we have plenty of time. Questions to ask.
Yes.
In n plus, you solve the degenerate elliptic equation.
Oh no, here this actually we only consider shock. So it's a strictly elliptic.
Strictly elliptic in n plus.
Yes, yes.
And then what happens in n minus?
Oh, it's a strictly hyperbolic.
And you have to solve the hyperbolic equation in n minus.
Oh, so hyperbolic equation, somehow this part known because in order to solve this part, you only need to know the data here.
So, but if you were to have a curved boundary, then you would have to solve the equation in n
Oh,
minus.
it's a good question. Okay, so the point is that in n minus, the Euler system is a purely hyperbolic. So you given this state, you solve the problem everywhere. And then you have to find out this transonic shock with the subsonic data simultaneously to match this with the already given supersonic solution.
So I guess my question is there any results for when you have to really do have to solve the hyperbolic equation?
Very good question.
Adjacent to an elliptic equation. Are there any mathematical results for that?
So the current case, so for Euler system only, for Euler system, when you have this kind of situation, always hyperbolic side first known and then elliptic side just determined accordingly.
Yeah.
But currently I'm working on the case when I have Euler Poisson system, where there is an effect of electric force. Then I have extra equation, which is a Laplacian, which affects in the supersonic and subsonic case both. So in that case, I really have to find transonic shock with the supersonic and subsonic at the same time. But I'm still working on it, except for that, I'm not aware of any results.
So, for example, one could imagine that interface is not quite like that.
Maybe.
It could be a
I mean,
bit of a
anything
mess.
is possible. So, anything can, I think,
Yeah,
cook up some.
Yeah, generally a two-phase problem.
Yeah.
One side the elliptical, other side have a body two-phase.
Also, actually, in order to answer your question, I don't think there's no result, but there are problems related to that. For example, if you have a contact discontinuity index, for example, there really supersonic side should be somehow affected by the subsonic side. Still, even that problem also open problem.
But I guess there are many, many numerical computations.
I think so. You're right. Yes, numerical result I think much more known this direction.
But different problems. Some problems numerically not so successful.
No, yeah.
Not the interaction of waves.
This nonlinear interaction, I think one should be extra careful. So. Okay, so thank you. Okay.